In a lab at Rensselaer Polytechnic Institute in the early 2000s, a farm kid named Eben Bayer was staring at a pile of agricultural waste that mushroom mycelium had quietly bound into a single solid mass, the same way he had watched it happen back home on his family's farm without ever thinking much of it. Most people would have walked past that pile without a second glance. Bayer saw building material. He and a classmate, Gavin McIntyre, spent the next several years figuring out how to make that natural process happen on command, in a mold, on a schedule. 5 days from spore to solid block, fireproof, soundproof, fully compostable when you're done with it. They founded a company around it in 2007. Why has it taken 20 years for almost nobody to have heard of it? Two things explain why a material this genuinely remarkable, grown rather than manufactured. Fireproof without chemical treatment and compostable at the end of its life, remains almost entirely absent from the insulation aisle at every hardware store in the country. One involves the actual biology of what mycelium is and why it can be coaxed into forming a rigid insulating structure in less than a week. The other involves the genuinely difficult economics of scaling a living organism into a manufactured product at a price that can compete with an industry that has spent 70 years optimizing fiberglass production down to the cent. By the end of this video, you will understand exactly what mycelium is, how two engineering students turned mushroom biology into a building material, what the research actually shows about its performance compared to fiberglass, and why the honest answer to when you'll be able to buy this at your local hardware store is more complicated than either the hype or the skepticism usually admits. The place to start is not with the insulation. It is with the organism itself, because understanding what mycelium actually is explains almost everything that follows. When you see a mushroom growing in a forest or a garden, you are looking at the fruiting body of a much larger organism. The way an apple is the fruiting body of an apple tree rather than the tree itself, and the mushroom cap represents only a tiny visible fraction of the fungus's total mass. The bulk of the fungus lives underground or inside its growing medium as a vast network of thread-like structures called hyphae, collectively known as mycelium. This network can extend for enormous distances. Some documented mycelial networks span multiple acres of forest floor and are among the largest living organisms ever recorded on Earth, older and more massive than many of the trees growing directly above them. The mycelium's job, biologically, is to break down organic material in its immediate environment and absorb nutrients from it, using enzymes to digest complex materials like wood, straw, and other plant fiber into simpler forms the fungus can use for its own growth and reproduction, functioning as one of nature's primary decomposers in nearly every terrestrial ecosystem on the planet. This digestive and binding process is exactly what makes mycelium useful as a building material, and it is worth understanding the mechanism precisely rather than treating it as unexplained magic. When fungal spores are introduced to a substrate of agricultural waste, straw, hemp, hurd, wood chips, corn stalks, or similar fibrous plant material that would otherwise be discarded, burned, or left to decompose slowly and unpredictably in a field, the mycelium grows through that substrate, digesting some portion of it for its own metabolic needs, and binding the remaining fibrous material together with an increasingly dense network of hyphae acting essentially as a natural self-generating glue. Left to grow for 5 to 10 days under the right controlled temperature and humidity conditions inside a mold shaped to the desired final product, the mycelium network becomes dense enough to hold the entire substrate together as a single semi-rigid mass with real structural integrity. At that point, the growth is deliberately halted, typically through the application of heat, which kills the living fungus and locks the current structure permanently in place, preventing any further growth and, critically, preventing the eventual emergence of actual visible mushroom fruiting bodies from the finished material once it is installed in a building. Stay with me, because the specific history of how this biology became a commercial insulation product is the part that explains both why the technology exists and why it has moved so slowly from lab to market. And the number I'm about to give you is exactly the kind most marketing for this material conveniently leaves out. In the early 2000s, to engineering students at Rensselaer Polytechnic Institute in Troy, New York, Eben Bayer and Gavin McIntyre were working on exactly this problem as part of their coursework and independent research. Bayer had grown up on a farm and had direct practical experience with the way certain fungi bind together loose agricultural material in nature. Having personally observed how mycelium naturally consolidates piles of farm waste over time, forming dense, coherent masses out of what would otherwise remain a loose, unstable pile of straw and other organic debris. Working with faculty mentorship at Rensselaer, the two students began systematically experimenting with deliberately cultivating mycelium on agricultural byproducts inside controlled molds, testing whether the natural binding process they had observed informally could be directed, standardized, and scaled into a precisely shaped, usable, manufactured product. Rather than occurring randomly in an open compost pile, the early results were promising enough that Bayer and McIntyre founded a company, Ecovative Design, and in 2007 filed a foundational patent covering the specific process of growing mycelium composites for use as insulation material. Marketed initially under the product name Griense, this represented the first serious, well-documented commercial effort to move mycelium-based materials out of purely academic experimentation and into a product with genuine fundable market potential, attracting early attention specifically because it addressed a problem: the environmental and health costs of conventional foam and fiberglass insulation manufacturing that was already drawing increasing regulatory and consumer scrutiny at the time. Here is where the story of the technology itself and the story of its actual commercial rollout begin to diverge in a genuinely instructive way, and it is worth understanding this divergence clearly rather than assuming the technology simply failed to gain traction for no discernible reason. Ecovitive's initial and explicit ambition was building insulation, and the company demonstrated working, functional applications quite early in its history. A widely cited architectural case study, covered by outlets including Arch Daily, described Ecovitive's mushroom insulation system being packed directly between wall studs in a real demonstration project, where the mycelium grew and solidified the loose particles into continuous air-sealed insulation within just 3 days in that specific application, simultaneously adhering to the surrounding pine boards on either side and creating what was described in the coverage as an extremely strong sandwich structure, comparable in performance to a manufactured structural insulated panel with no thermal bridging occurring at the stud locations, the way conventional fiberglass bat insulation typically experiences due to gaps in compression around framing members. But building insulation, despite this early technical success, turned out not to be where Ecovative found its fastest and most reliable path to actual commercial viability and sustained revenue. The company's own public account of its history describes a deliberate, strategic pivot. After pursuing insulation and broader construction materials initially as the primary focus, the founders found they could make the most immediate, tangible difference by tackling packaging foam instead, a decision made for entirely practical business reasons rather than any failure of the insulation technology itself. Their first commercially successful mycelium product became the foundation of mushroom packaging, a compostable alternative to polystyrene foam packaging material used in shipping fragile goods, which found dramatically faster market acceptance than building insulation ever did. This was true specifically because packaging decisions involve a much shorter sales cycle, far fewer regulatory hurdles to clear, and a far more straightforward value proposition that could convince a single purchasing decision maker at an individual shipping or e-commerce company, compared to the vastly more complex multi-stakeholder decision process involved in construction material adoption at any real scale, which typically requires simultaneous buy-in from architects specifying the material builders willing to install something unfamiliar, code officials who must approve it, and cost-conscious developers who need to justify the expense to project budgets, all before a single wall panel is ever actually purchased. This is the practical, genuinely unglamorous reason mycelium insulation has taken 20 years to reach almost nobody, rather than any grand conspiracy or industry suppression. It is not that the technology failed on its own technical merits, or that any competing industry actively worked to bury it. It is that the company that pioneered the technology found a faster, more immediately viable commercial market in packaging first. And building insulation, despite remaining the founder's original stated goal, has developed more slowly and deliberately as a secondary product line, pursued alongside the primary already successful packaging business, rather than as the singular central focus it might have become under different early market conditions. The mushroom didn't fail. The insulation industry just wasn't the fastest place to sell it. The mushroom didn't fail. The insulation industry just wasn't the first customer standing in line. Now let's talk honestly about the actual performance data. Because the claim that mycelium is simply better than fiberglass across the board deserves a more careful, evidence-based look than any thumbnail or headline can reasonably provide. Thermal conductivity, the measurement that determines how well a material resists heat transfer, and therefore how effective it is as insulation, is measured in watts per meter Kelvin, with lower numbers indicating better insulating performance per inch of material thickness. Standard fiberglass batting has a thermal conductivity around 0.04 watts per meter Kelvin, a figure refined over decades of manufacturing optimization. Mycelium composite materials, depending on the specific substrate used and the exact growing conditions maintained during production, have been measured in published peer-reviewed research at somewhere between 0.05 and 0.087 watts per meter Kelvin. On this specific metric, fiberglass is technically the better pure insulator, full stop. Mycelium is comparable to, or somewhat behind, fiberglass on raw thermal resistance per inch of installed material. And any honest, responsible account of this technology needs to state that plainly, rather than overselling a number that doesn't actually favor mycelium in the most. Straightforward apples-to-apples comparison, where mycelium genuinely does outperform fiberglass, and where the real defensible case for the material actually lies. Is everywhere else in the comparison beyond raw thermal number. Fire behavior is the clearest and most important example. Conventional fiberglass insulation, along with the foam-based insulation products that compete directly with it in the market, typically requires added chemical flame retardants to meet standard fire safety codes. And these retardant chemicals have themselves become a genuine subject of health and environmental concern in recent years, implicated in various independent studies examining indoor air quality and long-term chemical exposure inside homes over years of continuous off-gassing. Mycelium does not need any added flame retardant chemistry whatsoever to meet the same safety standard. When exposed to fire, the material carbonizes as it chars on the surface and forms a protective layer of carbon rather than igniting and actively spreading flame, the way many synthetic foam insulations can under sufficient sustained heat exposure. This is a structural, inherent property of the material rather than something achieved through an added chemical treatment, meaning there is no flame retardant chemical to potentially off-gas into a home's air over the material's lifespan. Acoustic performance is the second area of genuine advantage. Mycelium composite materials have been documented in multiple published studies to perform well as sound dampening material, a property that comes from the porous, irregular internal structure the fungal growth creates as it consolidates the substrate, which is more effective at breaking up and absorbing sound waves than the more uniform fiber structure of standard fiberglass batting. For interior partition walls in homes, offices, or recording spaces, this acoustic property is a genuine documented performance advantage independent of the thermal conductivity numbers. The third advantage is end-of-life impact, which conventional insulation materials handle poorly by comparison. Fiberglass insulation, once removed from a building at the end of a renovation or demolition, is not readily recyclable in most municipal systems, and typically goes to landfill, where the glass fibers persist essentially indefinitely. Mycelium insulation, being an organic material grown from agricultural waste and fungal tissue, is genuinely biodegradable and can be composted at the end of its useful life, returning the material to the soil rather than adding to landfill volume permanently. Fiberglass sits in a landfill forever. Mycelium goes back into the ground it came from. Here's what the honest current state of commercial availability actually looks like, because this is the part most enthusiastic coverage of mycelium technology glosses over. As of the most recent industry surveys, mycelium insulation remains available primarily through a small number of specialized companies, including Ecovative Design and the UK-based company Biome, with production capacity still described as limited and expanding gradually, rather than available at the scale of a typical big-box hardware store. Current retail pricing for mycelium insulation products runs approximately 2 to 3 times higher per unit than comparable fiberglass insulation. A cost differential driven, primarily by the smaller production scale, the specialized growing facilities required, and the heat pressing manufacturing step that locks the material structure in place after growth. which industry life cycle analyses have identified as the single largest contributor to the material's own carbon footprint. Somewhat ironically, for a product marketed on environmental grounds, industry analysts tracking this space have projected that broader availability and meaningfully lower prices are likely within the next 3 to 5 years, as manufacturing facilities currently being planned across North America and Europe come online and achieve the production scale needed to compete more directly with fiberglass on price. This is a realistic, moderate timeline rather than either the immediate revolution some enthusiastic coverage implies or the permanent niche status that skeptics sometimes assume. There is also a genuine practical limitation worth stating plainly. Mycelium composite materials are more sensitive to moisture than fiberglass, since the material is fundamentally organic and can be susceptible to further fungal or microbial activity if it becomes and remains wet under the wrong conditions. Unlike inorganic fiberglass, which does not support biological growth regardless of moisture exposure, this makes mycelium insulation in its current commercial forms better suited to interior applications and climates without severe sustained moisture exposure. Rather than a universal drop-in replacement for fiberglass in every building application without qualification. None of this diminishes what the technology actually represents, and it is worth ending on exactly what has been genuinely achieved, rather than only on what remains unfinished. A material that grows itself from agricultural byproducts that would otherwise be discarded, burned, or left to decompose unpredictably, using nothing but fungal spores, ambient temperature, controlled humidity, and 5 to 10 days of patient waiting, producing a rigid, structurally useful material with genuine, independently documented fire safety and acoustic advantages over the incumbent product it competes against, and returning harmlessly to the soil at the end of its useful life, rather than sitting in a landfill indefinitely, is a legitimately remarkable outcome of applied biology that deserves recognition on its own terms. The two students who first grew this material in a lab at Rensselaer Polytechnic Institute were not chasing a gimmick or a viral novelty. They were pursuing a genuine engineering solution to the environmental and health costs embedded in conventional insulation manufacturing. And the company they founded has spent nearly 2 decades since then scaling a fundamentally difficult manufacturing process, growing a living organism to a precise, repeatable specification at genuine commercial volume. With consistent quality control results, batch after batch, that conventional insulation manufacturing, built around inert materials and long-established industrial chemistry with a century of engineering refinement behind it, never had to solve in the first place because it never involved keeping a living thing alive and productive at scale. The mushroom does not know it is competing with a factory, and in a meaningful sense, it isn't trying to. It grows the way fungal mycelium has grown in nature for hundreds of millions of years, patiently consuming waste material and binding it together into a denser, more coherent mass, exactly as it does in any forest floor or untended compost pile on Earth. What has taken 20 years is not the underlying biology. The biology worked correctly and reliably in the very first successful lab trial back at Rensselaer. What has taken 20 years, and what continues today, is building the specific industrial infrastructure required to grow that biology reliably, at real commercial scale, at a price point that can eventually stand next to a roll of ordinary fiberglass insulation on the exact same store shelf, and win that direct comparison on more than just its environmental story alone. That infrastructure is being built right now, gradually and deliberately, in specialized growing facilities across North America and Europe that most people standing in a hardware store, aisle reading a fiberglass insulation label will never think to ask about or even know exist. The 5-day growth cycle itself has not changed meaningfully since that first successful lab trial in the early 2000s. What has changed, slowly and incrementally, is everything else required to turn that 5-day biological process into a consistent, reliable, competitively priced product, sitting on a shelf next to the exact material it was originally designed to replace. If you found this genuinely useful, watch the next video and do not forget to subscribe. See you in the next one.